Hello everyone, this is separation process course and this is part 2 of the topic liquid-liquid extraction. In this video we are going to discuss the first type of liquid-liquid extraction process, which is the single stage liquid-liquid extraction. In single stage, it's like we have only one stage, only one vessel. Okay. uh, yeah, so how we are going to, for example, determine the flow rates. If you remember from the previous video, we have the feed with composition XF, and then we have solvent with a composition XS, and then we have an extract with a composition XE, and then we have a raffinate with composition XR. Okay, so the question here, suppose we have the feed with its composition, we have the solvent with its composition, and inside the vessel we will have a mixture with xm, x of the mixture, composition of the mixture. Okay, so suppose we have this system and we are interested to know what would be the performance of our liquid-liquid extraction equipment. The performance means what would be the composition of the extract and the composition of the raffinate. Okay, how this extraction process will separate, to what extent. Okay, so suppose we want this, and also we want to know what's our production rate, what's E and what's R, what's our production, how much quantity we are going to produce from this extraction process. Okay, so to do this we need to apply what we have learned in the previous lecture. First we need to have some data that is usually collected from literature, or it should be provided. These data that you need in order to apply the upright triangular method to calculate XE, XR, E and R. Okay, so this data is mainly composition of A and composition of B. In other words, composition of a solute and composition of the solvent. So you need to have this data, and also you need to have equilibrium data, as we discussed in the previous lecture, the equilibrium data between the composition in the extract phase and the composition of the raffinate phase. Okay, so the first set of data, you will use them in order to develop the component diagram, and other data you are going to use them in order to construct phase diagram. Okay, so how we are going to do this? You need to plot them together. It's gonna be much easier for this type of problems where you have a single stage liquid-liquid extraction. So what you do, first you draw your upright triangle, okay, and beside it you draw your equilibrium curve. Okay, so you start doing this and then you specify the axis. So in upright triangle, this is from 0 up to 1 or 100% of B. And again, for the y-axis, this is from 0 up to 1 or 100% A, which is solute. So the remaining corner, would be the carrier. But we don't need this carrier in developing this diagram. Okay, so we have the data you need to have data of xa and xp, then you can plot them. For example, if you have xa is 0.1 and xp is 0.2, then you move like this. So 0.1a, for example, 0.1a, whereas 0.1a is something here, something here, and whereas 0.2b, something there. So plotted, so this is our point here, and you complete all the points. Okay, so suppose you did this, so you will get a curve like this, somewhere like this. Okay, let me do it like this. Okay, so you'll get something like this, and then you go and draw your equilibrium curve. So you start by the 45-degree line, and then you draw your equilibrium curve using this set of data xe and xr, and again the x-axis here would be x raffinate as a convention, while y-axis would be x of the extract. Okay, and then you draw it. It would be maybe something like this or whatever. Okay, then what you do, you start after drawing these two diagrams, you start by specifying your feed point, your xf and xs, these two. Yeah, these two, your xf and your xs. Okay, and as we agreed before, xf and xs both are for solute, for a, both are for a. Okay, so since they are for a, so you need to specify them. You need to look at your axis, your y and x axis on this diagram. Okay, so suppose for example the feed contains approximately, for example, it contains 60% A, 60% A and 0% B. So where is 60% A? Maybe somewhere here, 60% A. Okay, and where is 0B? Yeah, 0B is here. So this gonna be our point for the feed. This is XF. Okay, and then you specify XS. So suppose your XS is 100% B, it is only B, there is no A. So for example, point will be somewhere here. Okay, then what you do, you draw a line between XF and XS. You draw a line between XF and XS. So it would be something like this. Okay, so this is the first step. And then what you do, you need to determine your xm, and how to get this xm, again by simple material balance. As we discussed in the previous lecture, we have f plus s is equal to m, and we have xff plus xss is equal to xmm, right? And we should know our feed and our solvent, so we can get m, and then use this m here, and you should know your xf and your xs and f and s, and you calculate already m from here, so you can get xm. After you get your xm, suppose you get it, for example, let's say you got it for example, let's say 40% A. Then you go and look. For A, you look at the y-axis. Okay, so 40% will be somewhere, let's say somewhere here. Somewhere here. Okay, then what you do, you look at this blue curve, then you draw a horizontal line, okay, and then the intersection with this blue curve that we already drawn between xf and xs is going to be your M point, your mixing point. Okay, so the intersection, where is it? Somewhere here, right? So this point, gonna call it, this point is called M. M point refers to mixing point. Mixing point. Okay. Then what you do, you start from any random. By the way, this curve, this one that's close to B is called extract curve. Extract curve. And this curve that's close to the carrier is called the raffinate curve. Raffinate curve. Okay, so what you do, you start by an extract curve. Start at any point, and then what you do, you move horizontally. Move horizontally until you hit equilibrium curve. You stop, then you move vertically down. Okay, then you go back. You go back, but not back to extract curve, no, back to raffinate curve. And then you connect the initial point and final point like this. Okay, this line that we have just drawn is called tie line. Tie line is simply a line that connects the composition in two different phases. And as we agreed in liquid-liquid extraction, we have two different phases, two different liquid phases. So the line that connects these two compositions and these two phases, the extract phase and the raffinate phase, is called a tie line. A tie line. And what's the benefit of this tie line? To know the benefit of this tie line, we need first to draw a tie line in such a way that it hits the mixing point M that we have already determined. Okay, so again, we want to draw a tie line that hits this mixing point. Okay, so it is like a trial and error. Trial and error. So in our first trial, we did not hit the mixing point. So what we do another trial. For example, let's say we start, for example, from, and previously we started from here. So let's start from other point. Let's start, for example, from here. Let's start from here. So what we do, we draw a horizontal line until we hit the equilibrium curve. Then we move vertically. Then until we hit 45-degree line, then we move horizontally back to a raffinate curve. Then we connect the initial point with the final point. Okay, see, if we connect them, yeah, we hit L mixing point. We hit the mixing point here. We hit the mixing point. So we stop. So this is our target tie line. This is the tie line that we want. But the question here is, what's the benefit from this tie line? Simply, the benefit is that from this tie line you can get XE and XR, our benefit, our target, XE and XR. How to do this? As simple as this. See this tie line? Whereas this tie line hits the where this tie line hits the extract curve at this point, right? So this point, then you move horizontally. The value that you are going to read from this axis is gonna be your XE. And similarly, where this tie line hits the raffinate curve, it hit it here. So again, you move horizontally, and the value that you are going to read from the y-axis is gonna be your XR. So doing this, you can get your XE and your XR, and this is our target. Okay, so the question here, okay, we get our XE and our XR, but how to get our E and our R flow rates? To do this, again, we do a simple material balance exactly as we did in the previous lecture. So we would say F plus S is equal to E plus R, and then XFF plus XSS is equal to XEE plus XRR. Okay, so how many unknowns we have here? And suppose you know the feed and the solvent, XFF and XSS, all of this are known. So how many unknowns? We don't know E, we don't know R. We don't know E, we don't know R. And XE, XR, now we know them from this tie line. So we know XE and XR. So you have one equation, second equation, we have two equations, two unknowns, R and E. So we can solve them simultaneously to get E and R. And that's it. So doing this, you can get your XE, XR, and E and R flow rates. Okay, and you can solve the problem. So that's all for single stage liquid liquid extraction. In the next video, we are going to discuss the second type of liquid liquid extraction process, which is the cross current multi-stage liquid liquid extraction. Thank you for your listening. I wish you all the best.